Now that we've seen a couple of useful combinational logic functions, namely a decoder and a multiplexer, let's talk about how you can take any logic function and create the gates. Now, sometimes you want to create a custom logic function, something that's not a standard function such as a decoder. And that custom combinational logic function is defined by its truth table. So here's an example here where I have a function which has three inputs, a, b, and c, and this is the function f. And here are all the possible input combinations. And here I've put zeros where the function is 0 and 1 where the result is 1. So this is just an arbitrary function that I've created. And what we're going to do is we're going to take this and we're going to put down the NOT and an OR gates that implement this truth table. So first of all, let's talk verbally about what this function means. Now, you can do this in two ways. You can focus on the zeros of f, or you can focus on the ones of f. So let's focus on the ones. So verbally, what this function means is f is a 1 if a is 0 and b is 1 and c is 1, or a is 1 and b is 0 and c is 0, or a is 1 and b is 1 and c is 1. Okay, so you can see that we have some inversion. So if I have not a here in this particular row, and then you see we have the ANDing of these different inputs, and then we also have an OR because it's a 1 if any of these combinations are seen on the input. So what we need to do is, first of all, is we need to create a set of AND gates that detect each of these rows where we have a 1. And you see that we're going to have to invert some of our inputs in order to do that. So we're going to do the same thing that we did with decoders and multiplexers. We're going to draw this out with the inputs at the top or the bottom. You can choose which way you want to do it. I'll just put them at the top. So I have my inputs A, B, and C. And we're just going to run these wires down this way because we're going to tap off of those. And then we're going to create the inverted value because we may need that as well. So we're just going to take A, we're going to put it through an inverter, so we have that available. And we'll do the same thing with B and C. Okay, so now I have the true value of A available as well as its complemented value. Okay, so when A is 0, then this is going to be a 1. Okay, and obviously if an A is 1, then this is going to be a 1. Okay, so let's look at this first row here. We have a 1. So I have when A is 0 and B is 1 and C is 1, then I will have a 1. So what I need to do is I need to take the complemented value, because when A is 0, this is going to be a 1, right? So I need to take that complemented value and put this into my 3-input AND gate. So I take the complemented value of A and feed that in. And then for B and C, I just take them their true value. Okay, so I take B from here, and I also take C from here. So this AND gate is going to be a 1 if I have 0, 1, 1 on my input. Okay, and so we do the same thing for the other two rows. Okay, so let's take this row here, make another AND gate. And here we have A is a 1. Okay, that's when we get a 1 here. So we're going to take the true value of A. And here we have B and C are 0. So we're going to take the complemented values of B and of C. Okay. So again, this output's going to be a 1 when I see 1, 0, 0 in my input. And finally, in the last row here, when I have all 1s, so I just take the true values. This is my last AND gate. So I take the true values of A, of B, and do this very carefully. Sometimes you can make mistakes and take the wrong ones. You have to be very careful. And C. And here's my last AND gate. So you see that because I have 3 1s in my truth table, I have 3 AND gates. And because I have 3 inputs, then each of these AND gates has 3 inputs. Now what we can do is we can do an OR of this, because remember we said that if we see this input pattern, or this input pattern, or this input pattern, then F is a 1. All we need to do is to add a 3-input OR gate that collects all of these AND outputs. And this is our function f. Okay, so you can take a truth table, any combinational logic truth table, and you do this procedure of taking the true and complement values as appropriate, feed them to a first level set of AND gates, and you have as many AND gates as you have ones in your truth table. And then you have an OR gate which is as wide to collect all of these ANDs. And that's how you implement f. And you can do this with any truth table. Okay, now if you recall, with CMOS, we said that we have a NOT, we have an inverter, we have a NAND gate, and we have a NOR gate. Okay, so those are the best gates for CMOS. Well, what I have here is I have an AND and an OR. Okay, but we can convert these using De Morgan's law into NAND gates. So how do we do that? Well, first let's convert this into a NAND gate. So if you remember the symbol for a NAND gate, this is a NAND. I put a bubble here at the end. Okay? So now I have NAND gates at the first level. Let's convert this into a NAND gate. If you remember from De Morgan's law that an OR with the inputs inverted is also a NAND. So this is also a NAND gate. Okay, so I have a NAND gate here and a NAND gate here. Well, why does this work? Well, I hope you see that these bubbles cancel out. Right? It's like they're not there, because I'm going to invert this output, and I'm going to invert it again. So this is exactly the same function as having the ANDs and the OR. Okay, so we can build a combinational logic function like this using just inverters. We're going to keep inverters around because they're very fast. There's only 2 transistors here. And then all we have to have here is NAND gates. So in CMOS, we can build any function using just our inverters and just our NAND gates. And we can also do the same thing if we focus on the zeros. What we'll end up is with just inverters and just NOR gates.